I think we'll go ahead and get started. Thank you all for being here today in person and on Zoom. I know today's not our normal seminar time, so I really appreciate you taking the time to come out here. And for those in person, we do have some goodies in the back there. So please make sure to grab some, especially on the way out, because I think we'll have some extras. But today it's my pleasure to introduce Oliver Schmidt, who is coming to us from UC San Diego. Oliver was actually here as a student many years ago, but we're so glad that we can convince him to come back, and we actually have some really amazing weather for you today, seeing as we don't have the classic Seattle rain. But today Oliver will be talking to us about different data-driven methods and reducer model methods for fluid mechanics. And with that, I'll just go ahead and let Oliver take it over.
Well, yeah, thanks a lot. 21 years now, and I see a familiar face, blast from the past. I took your viscous, this is called viscous fluid mechanics course.
My sympathies.
Yeah, that was a good class. That was a good class. A lot of fond memories from my UW plans back then. Last night I walked over the app. I couldn't recognize anything, not a single building, didn't find one single food place that I liked. And it's changed a lot. Okay, well, thanks a lot for the invite, Steve, for organizing, and the invite, Nick. You already introduced me, Oliver Schmidt. Today I'm going to show you some work of 3 of my students, Brandon Young, Tianyi Chu, and Eden Shokogoza. I'm going to talk about data-driven modeling for turbulent flows. I'm going to focus on 2 specific things. Here are the 3 main protagonists, Brandon, Tianyi, and Eden. I'm going to start by just, talking about some challenges of complex flows that I would like to address. We use modal decompositions a lot to provide a basis, a latent space for model order reduction, but also just for physical exploration to understand the flow physics. Then I'm going to talk about the stochastic Hofmann reduced order model we devised based on STUB. That's why we're going to do a little example. Look at how that works. Then pivot back to modal decompositions, talk a little bit about how nonlinear interactions can be incorporated, and then I'm going to talk about the triadic orthogonal decomposition. So you might be asking yourself, well, where's my AI? This is the AI Institute, and the honest answer, right? So this is from 9 a.m. this morning. It's just not working. Okay, I want to talk about fluid mechanics and model order reduction and so on. So Brandon, that's it. So everything I'm showing today, that's stuff he did on the side. His main project is machine learning. Jet noise reduction for twin rectangular jet for the Navy, and blah. Fortunately, doesn't seem like training reward is going up at all. Yada yada. Episode 200 is even going downwards. Blah blah. I forgot your okay. So I'm not going to talk about that. Let me fire up these videos here. So here's this on the bottom right here. That is actually Brandon's flow. So that's what he is trying to apply reinforcement learning to. The problem is it's on the very, very right of my nastiness scale here. So nastiness, it's proportional to the Reynolds number, but there's other elements to it, and one of them is, for example, multi-scale aeroacoustics are nasty multi-scale problems where the fraction of a % of the kinetic energy in this flow gets actually translated into acoustics, so it's multi-scale. On the left here, we are in our peaceful linear laminar one-dimensional world, and it gets maybe 2-dimensional. We can see the nonlinear dynamics, low cylinder flow. And these are flows I'm going to all show you today, but for the nastiest one. Then we are 3-dimensional as a transitional flow, so we get into the turbulent regime, but we still have Z periodicity here, Spanner periodicity, so this is nice clean DNS data. And then the data gets messy. This is experimental data, time resolved PIV, so that has gaps, that has a high signal to noise ratio, and so on. And then this last one that I forgot to animate, that's again a clean simulation, but it's 3-dimensional and it's fully turbulent, but it's cylindrical, so there's some symmetry in it. I'm only going to talk about stationary flows, wide sense stationary flows. Fully turbulent, but stationary flows today. I'm not going to go into transient intermittency, extreme events, multi-scale, and so on. So the basis of these methods we're working with are model decomposition. So here's my very quick, broadest overview. The big two, POD, right? Eigenvalues of the autocovariance matrix, optimally ranked by energy. The coefficients are real, but if the process is random, the coefficients are random. DMD has the nice advantage that it gives us complex frequencies, so we can have decaying, amplifying, or neutral modes, but there's no natural order to DMD modes. The link to Koopmanism is, of course, a huge advantage when it comes to model order reduction. And then we have the good old Fourier transform. Of course, that it orders by frequency, at least intuitively. The frequencies are real, so everything is oscillating at one single frequency. But the Fourier transform for stationary data, for chaotic data, is just not converged, right? It has no convergence properties whatsoever. But we can do a little better by spectral proper orthogonal decomposition, which is proper orthogonal decomposition in the frequency domain. It's computed from the Fourier transform. And it's going to be the main building block of the model that I'm going to present. And I found that the easiest way and the quickest way to explain SPOD is actually through the algorithm. Here's the algorithm. We start with a snapshot ensemble, and you can just imagine this as a video, right, that plays from here to here. So this is the time direction. We have 1, 2, 3 spatial dimensions. Doesn't matter. The first thing is we want to go to the frequency domain. But the first thing is we're going to segment this data. We're just going to chop it into segments. And these segments can overlap. Let's say we have 10,000 frames. Make each of these 256 long and make them overlap by 20. Pick a number, right? So then we have many kind of building blocks. What we're leveraging here is the ergodicity of this process, right? So now we're taking the Fourier transform of each of these blocks individually. So we get the number of frequencies that corresponds to the number of snapshots we had in each of these. Divide this by 2, -1 or not, depending on even or uneven, right, to get just positive or negative frequencies. And now we argue that if everything is nice and ergodic and wide sense stationary, each of these represents an independent realization of the Fourier transform. So what we do now we just do a good old POD. We just rearrange things a little bit. We just build data matrices for each frequency. I'm taking the third frequency out here, the third bin, and I'm putting it into one. I'm flattening the vectors and I'm putting them in the data matrix, one for each frequency, and then for each of these, we can build from the Fourier realization matrix, data matrix, we can just compute the autocovariance matrix and then take an eigenvalue decomposition, and that is just then a POD. But but one POD, one set of eigenvectors and eigenvalues at each frequency. And then we can invert the whole process. That's just a bunch of linear algebra. It's a little bit non-trivial because of this blocking. You have to somehow invert this and stitch this whole thing back together to get our video back. So there's a little trickery involved to make this kind of smooth, right? But it's absolutely possible. It's described elsewhere, but we're going to need this later. So that's how it works. Here's a simple example. Classical cylinder flow, low Reynolds number, 100. Parameters are not that important. What's important? Well, we recorded 4,800 snapshots here, and we're going to chop this into 8 blocks with some overlap. Now we're going to compute the SPOD, and that gives us 2 main results. It gives us a spectrum, and it gives us modes. What gives us spectra? Because now, so lambda, just think this is mode energy, right? So this is the POD property ranked by mode energy. Mode 1, mode 2, mode 3, mode 4 until 8. Each get their own spectra. You can see that they're beautifully converged. You can see adding more doesn't help. We can now run into the noise floor, into the machine precision down here anyways. These are nice and smooth. That is just dimensionless frequency. Should have replaced this, right? Just dimensionless frequency. So we get the spectra, mode 1, mode 2, mode 3, and so on. We see these peaks. Obviously, this comes from the simple vortex shedding dynamics. We got our Van Karman vortex street. This is the fundamental first higher harmonic, second higher harmonic, and so on. This is why we see these peaks. And then, of course, we also get the corresponding flow structures. And the nice thing about SPUD, right, this example is trivial because it's all laminar. But if we would do the same thing at Reynolds number 1 million, we would still recover, if we have enough data, these nice statistically converged clean structures. So that's the big advantage. So it tells us which frequency components are most energetic. It tells us something about the structure of these, the wave numbers, the scales. And it tells us something about the low rankness, right? These are orders of magnitude in between. You can forget all of this, right? Probably just taking these peaks, that describes 99% of the entire energy of this flow. Okay, doesn't tell us anything about the interaction, right? So this is the power spectrum. If you ever took a signal processing class, right? Well, or you don't even need it, right? You square something, right? If you remember in PUD how you compute the eigenvalues, this is the expansion coefficients times their own conjugate absolute value, right? If you square something, you lose all phase information, right? So we do not know how these are related to each other in the time domain. They live in the frequency domain. Okay. So now Tiannis, that was also a side project. Tiannis will also work. Everything interesting I do is a side project. So it's the stochastic SPUD Koopman model that Tiannis ironed out, and we're going to apply this to two flows that are not easy to deal with for different reasons, right? So we got the experimental data that already tells us we have to go data driven, right? This is one slice out of a three-dimensional cavity flow. But the PIV, the laser sheet that lives in one single plane, so that you can't even data assimilate this. I mean, maybe a lot of trickery, but we want to work with the raw data. And this is just a two-dimensional cut, but this three-dimensional a large eddy simulation of a fully turbulent jet. So here are all of the challenges, and here how we're going to address them. Of course, we're going to walk through the entire algorithm. High dimensionality, we're going to use, that's why I just talked about the SPUD, we're going to use the SPUD for latent space compression. So we're going to, we will evolve in time the SPUD expansion coefficients via a Koopman propagator. The time delay, memory effects, nonlinearity, and so on. That's kind of baked in because if you think about it, the SPUD lives in the frequency domain. To go forth and back, we always need a finite time horizon. So by definition, by construction, this model is going to be convolutional in nature. These flows are turbulent. They're stochastic. This one even has noise. We're going to devise a stochastic model that has random inputs that are then colored to give us the correct color of the noise. Nonlinearity in particular, we're going to address by state inflation. I'm going to explain what that is. And the turbulence closure is a stochastic residual closure via de-whitening filter. Okay, this is just to put things into perspective. That was for ourselves to understand where do we live here, right? So this isn't, why do we pick SPUD for model order reduction? This is just an overview of model decompositions. You find all colors of PUD, space-time, valence, yada, yada, all kind of operator-based methods. Stability theory is in here. Pick whatever you want. Balanced fluctuation, linear theory, Koopman theory, BMD, right? And what makes SPUD interesting is two things, right? This is in this direction. This is where we live in terms of kind of what type of system are we dealing with? Linear system, forced linear, nonlinear. The spectral PUD modes, it's a linear decomposition. There's nothing nonlinear in here. But it lives at this interesting intersection of dynamics, everything that has a DDT, and statistics, everything that is average. It kind of has both, because we can get discrete time continuous expansion coefficients for these statistical objects that the SPUD modes are in the frequency domain. Okay, so this is just to put things into perspective. So the state is going to be just a superposition of our SPOD modes, right? So instantaneous flow field is just going to look like a sum of SPOD modes with time-dependent expansion coefficients. And we're going to take this, right? So here's another reason. Spectral POD has a theoretical relationship to resolvent analysis. What is resolvent analysis? Not going to talk about this, but it's basically an LTI system, forced LTI system interpretation of the Navier-Stokes, right? An input-output interpretation. This is how we can see it. So this is exactly what we're going to use here. So we're going to write our LTI system for the SPOD expansion coefficients in the time domain, right? I'm going to propagate them linearly, and then we have a residual. So these are our expansion coefficients that are convolutional because we have to integrate because the modes they have the time exponential in their definition, right? So they live over a number of periods within the block size we selected. So we have to convolve them over the data to get discrete time continuous expansion coefficient. If you look at this screams Hilbert, but you actually don't need it. It's all built in. So this is what we're going to propagate, and then go back to the physical space by just expanding. We're just going to use a coupon operator, compute it in the usual way, d square with L2 regularization, to get it, to propagate it. But then, of course, this is not going to be a good model. It's a coupon model. It's either going to blow up or decay. It's not going to be useful. We're going to interpret the residual and the resolvent idea as a forcing to the system. For closure, we're going to inflate the system. This is a very neat little trick. So we don't know much about the residual, so why not just add it to the state, inflate the state, and also propagate it by two propagation matrices that we will identify in exactly the same way as the coupon operator, least squares L2 regularized. This is sometimes called the linear inverse model by Penland. So then it looks like this. We have the inflated space. We have to identify, we have to compute also from the data these two matrices. However, after this, we probably still have a residual. So we just add yet another level. So this is level 1. This is the level 2 residual. Now what we could do is, well, we could slap the R on our state vector and can continue and continue and continue. And you can absolutely do that, and it actually works. The magic is that sooner or later, we will be able to model this. We can't model this or kind of nonlinear Navier-Stokes business going on. At some point, this is going to become Gaussian white noise. That's the hope. And even for these very complicated flows, it happens at the second level. So we will model this residual via a white noise input that goes through a de-whitening filter that gives us exactly the right statistics we need to drive our system to get some physical outputs. So it's because of the stochastic input, we use a stochastic Euler Maruyama time integrator, and then we can just multiply this with G, plug in our time integrator, solve it, and then we get a formula for this kind of Kolyatsky factorization like confidence covariance, right, of G, and that we can just compute. And that gives us a matrix that multiplies our white noise input and gives us exactly the right color of noise to feed into this system and drive it forever. Don't have to talk about all of the parameters here. There's the two regularization parameters. We get away with 10 to the minus 3, 10 to the minus 4 in both cases. So it's not sensitive to that. That's kind of nice. We're going to look at the Pearson correlation just to see how fast does the solution deteriorate from the true solution that we have, and the good old root mean square error. So here's just this is an animation. This is instantaneous, just of the forecast, just the visualization, right? So the jet moves from left to right, it's a jet, so it decelerates. So these structures are hardly moving. These structures are moving faster, right? So you can try to compare the reduced data model to the forecast. Same here. And what you're going to see is the model. Okay, so I need to call it SLIC, which it stands for stochastic. I forgot. Low dimensional inflated convolutional Koopman. So it's not even that. He promised me he didn't use ChatGPT. Anyway, so it produces a forecast. This is of course just eyeball norm that looks somewhat realistic. Of course, we have to compare to the reduced order data, not to the full data, right? We truncate it somewhere at rank 25 or something here, and in frequency. This is the quantitative comparison. I know it's a little much. Left is still the turbulent jet. Right is the open cavity flow data. The top three rows are just three different frequencies, low, medium, high frequency. The bottom is some integral quantity of interest. This is the pressure integrated over the entire domain. This is the turbulent kinetic energy integrated over the entire domain. And what we're going to see is the model itself in blue, the line in the middle, the data, the truth that is in red. That's what we want to model. These are models that look so sinusoidal because these are the expansion coefficients of the SPUD modes. The forecast starts at some specific time, not at zero. Well, it starts at zero here, but we have to go in the past. We need the past data because it's convolutional. Right? So we need half a block size in the past of data to fit the modes that actually evolve over a finite time horizon, and then make a forecast with a small error at zero. And then the model lends itself very naturally to uncertainty quantification. You can do Monte Carlo, right? So then we get these bright light blue envelopes, but we can also, this is the dash line, solve a Lyapunov type of equation and get it directly from the model. So this is how well it predicts. You can see it follows pretty well over pretty long time horizons. The overall error, of course, right? We lose our predictive capability after a few non-dimensional time units, but that's to be expected because these flows are just fully turbulent, messy. This is just averages of the RSME and the Pearson correlation, right? At the start here, right? So RMS is in red. We get training and testing data, right? So we want it to be fair. We learn from the AI machine learning community a little bit. So we can just look at the testing data that the model has never seen, right? So the error starts low, and then of course at time zero it starts ramping up. The correlation that between the testing data and the model forecast, that of course goes down. But as you can see here, over about like 5 non-dimensional time units, this is for the turbulent jet, we get forecasts that one would still deem kind of acceptable in the acceptable level. So the model worked surprisingly well. Another thing it does, because of how we constructed using this inflational multi-level approach, it reproduces the statistics correctly. So we can use it to create surrogate data as much as we want. That it's stable. Magically, if you're good at math, maybe you can derive it. We weren't able. The regularization, not just the regularization, but the inflation pushes the eigenvalues on the unit disk. The model just stays nice and stable. You can integrate that until the end of days, and then compute your SPUD, and it recovers the correct second order statistics. So that's really nice. So this is a little bit of an overview of the model, how it's built. Koopman operator involves convolutional coordinates, and so on and so forth. I think that the most fascinating part is probably the whitening filter, right? That this kind of provides us turbulent closure in a very automated way, right? If it wouldn't have worked at level 2, we would just have went to level 3. Haven't found a flow yet where it doesn't close early, so that's kind of nice. Accurately predicts over very short time horizons, so weather forecasting, but it generates realistic surrogate data forever. So it's also So people have started using it for turbulent inflow generation and these kind of things. And Monte Carlo is kind of uncertainty quantification is kind of built in. It's kind of inherent. So that's a nice goodie we get. Okay, the second topic is now we're going to go back to, so now we used SPOD, and these two, they're kind of, I would say, complementary, but also a little bit different. The two topics that I want to discuss. Now we're going to talk about how can we incorporate nonlinearity directly into our modal basis. This was work by Brandon as well and Gianni into one decomposition. So these are the three we discussed. This on the right here, there's kind of an earlier attempt, I forgot to republish this, 2022, to derive a decomposition that gives us, that provides us the interaction, the triadic interaction of different modal components of the flow, spectral components. And this was still built on was kind of a modal decomposition extension of the signal processing concept of bispectra. So this does not take into account, what is it just looks at, is there quadratic nonlinear interaction? Is there triadic phase coupling or not? That's all it tells us. But now we extended this to the triadic orthogonal decomposition, which gives us a lot more information and is specific to the Navier-Stokes. To put it into perspective, here's my little overview table of modal decomposition capabilities. All of them give us structures, spatial structures. So otherwise they wouldn't call it modal decomposition, I guess, because these are the modes. Time dynamics, well, POD not so much. Well, whenever you see an X here, sure, you can somehow ad hoc hack your way to get expansion, but they're not inherent to the decomposition per se, right? That's all I'm saying. Whereas SPOD, Fourier, DMD, they give us frequencies, real or complex frequencies. BMD gives us real frequencies. The TOD gives us real frequencies. These methods, that's also one of the reasons why I kind of hopped on, the SPOD algorithm. They're computed in a very, very similar way. There's different ways of computing it, but the vanilla version that I showed you earlier, the spectral estimation by segmentation, we use this for the first versions of these methods too. Optimality, they all have it, but poor DMD, right? That's just it's based on an evolution operator. It's a little bit different. Nonlinearity, only the last two, because they were designed for this purpose. And what TOD adds, the last capability, it actually tells us about the energy transfer between the structures. So that was kind of the last missing piece. So on POD, we get energetics, spectral energetics from SPOD, dynamics from DMD, hence the name. Nonlinear coupling from the BMD, and nonlinear actual energetics from what I'm going to show you now. To get the energetics, we have to use the Navier-Stokes. We have to use what I learned in your class. No, right? We always took a curl, right? I think we always use. Right? We always work with the vorticity equation. We're not going to take the curl. So this is just our momentum equation, just in the frequency domain, right? You just take the Fourier transform, the DDT becomes I omega, U, and so on. N is the frequency index. That's the N frequency. This is our convolution sum. That is the convective term, right? And we have our pressure and our viscous term. And this gives us the directivity information. I'm gonna explain that in more detail later. It's interesting. And to get the energy, we need the energy equation. So again, we're not going to take a curl, but at least we're doing something. We're left dotting it with UN itself, or the conjugate of it that gives us the energy equation if we take the real part. Right. So this is the spectral K equation to get the energy transfer out of the transfer term. Okay, these are the two ingredients. How do we get a directivity out of the momentum equation? So this is the momentum equation. I color-coded these. This is our convective term. We're going to abbreviate it as CL2N. L2N implies from frequency component L to frequency component N. Why are we allowed to say this? Why can I call this the recipient? Well, that's maybe okay, right? So because this is the left-hand side, so this equation governs the end frequency component in our harmonic balance here, right? So this is kind of what comes out, but these two go in. So how can I discriminate one over the other? Why can I call this one just a catalyst and this one the donor? It's actually, there's a simple kind of proof. You can actually show there's of course symmetry, right? So I can swap these. I can swap these indices, right? I can look at the equation for the L component that should have the n somewhere. But the one thing that doesn't change if we actually integrate and look at the energy is this guy here. So we can call this the catalyst because it's just not involved in the energy exchange. It's only these two modes. All right, so the advective field and what we have on the left-hand side. And then we can draw these kind of Feynman type diagrams. So here's the problem. This we just took straight from POD. We'll just extend a little bit, right? POD is an autocorrelation, but what we want is a cross correlation. So we want to jointly maximize the correlation between projections of the convective modes, the right-hand side, and the recipient modes, the left-hand side, onto our equations, right? So then we get an optimization problem for two different bases. So we have a convective mode basis, the recipient basis. And we want to maximize this quantity, which is just the convective recipient correlation or covariance if we normalize it. And this normalization problem has a very simple problem, a very simple solution. You can guess it. It's an SVD problem, just like POD. An eigenvalue problem. This is a pure pure SVD problem because it's non-Hermitian, right? So BMD, for example, there was yet a different problem. There was a spectral range problem. This is just a singular value problem for this cross bispectral correlation tensor that we built between the right-hand side, convective, and left-hand side, our nth component, our recipient modes. So we just solve this, and then we can get, after a bit of derivation, we can actually compute the t-term, the average energy transfer between modes from the modes themselves, weighted by their covariance. And we can plot this as an energy budget. So everything we're going to show, well, we're going to have modes and we're going to have a spectrum. Just like for SVD, only our spectrum is now, because there's always three frequencies involved. Two, the recipient and the donor. The third is the catalyst. So we plot this in the bispectral plane, frequency over frequency. Then in however you want to visualize it, here we just use these kind of polka dots and color coded the cross covariance, how large it is. You get this polka dot pattern. This is for the cylinder flow. So we get these like nicely separated because this is the fundamental first harmonic, second harmonic, and so on. You can just check how they interact, right? How much do they correlate, these different frequency components in the flow? This doesn't tell us anything about the direction of the energy transfer yet. It just shows us, are these frequency components triadically coupled or not? To get the energy directivity, we need the energy budget. We're going to focus on the transfer term. Of course, there's also there's pressure work being done, there's dissipation being done. We can compute all of this, but the energy transfer that happens only in the spectral version of the convective term here, right? So that's our energy transfer term. What's usually done is the two ways of thinking about it. Either you think you're a classical fluid mechanicist and let's pull out the mean that's always special and look at that separately. So the mean is the U bar, but we're already in the frequency domain, so the mean always ends up in the zero bin anyway. So it happens naturally here. But it helps with the physical interpretation to separate it out, right? So if we look at the terms that involve the beam, then we get one where the mean transports the fluctuation, the non-zero frequency component along its gradient. That's advection. If we flip these two, then we get production. but everything else is nonlinear transfer interaction between two frequency components. If we look at the zeroth energy from zero equation, that's the mean kinetic energy equation, and we can identify an advection term, a nonlinear transfer term, a pressure work term. This looks familiar to fluid mechanicists, right? So that's the Reynolds stress tensor. And we have pressure work and dissipation. We don't care much about here. Again, we can plot this as donor axis. Again, I'm just pretending there's a fundamental, there's twice the fundamental simple dynamics. We can plot this over the recipient frequency. We can read the catalyst frequency of this diagonal. We can read linear advection of where the catalyst is 0, transport by the mean. So this is where we can read linear advection of. Because of the Fourier symmetry, the conjugate symmetry, we only have to, everything down here is redundant, so we can only look at the top. We can read the production of the recipient axis here, and we can read the mean advection of the origin. So every single term in the spectral K equation, we can read off this one diagram and we can get the structures involved. So here's the modal energy budget, right? So now we have colors. Red says energy goes from donor to recipient, blue the other way around, right? So you instantly spot a symmetry, right, along this line. This has to do with the symmetries of the conservation of the triadic energy transfer. So you can write all of this out and then see it analytically. So interpretation is just a little interpretation guide that I like giving. If we see red, this means energy goes from donor to recipient. If we see blue, then energy goes from the recipient to the donor, right? The two components just change their roles. So if in this sector everything is red and in this sector everything is blue, or if we have a pair that looks like this, right? Then the donor frequency is lower than the recipient frequency. That's a forward energy cascade. Right, so a vortex breakdown, right? So classical turbulence. If it's flipped the other way around, then we get backscatter. This means that energy is going up the cascade. For example, vortex pairing is the most kind of intuitive example of this. Energy can only enter or leave the system through these two axes. In here, energy is only redistributed amongst the model structures. All right, so here in this little example, this is for vortex shedding and 100. I'm going to show you two examples. One is the vortex shedding and Reynolds 100. That is kind of only to kind of build a little bit of intuition into structures are so nice and clean and interpretable. Then I'm going to show you like a more kind of intricate example that's a little more spectacular. All right, so we get the vortex shedding, first higher harmonic, second higher harmonic. Right, we can look at those from the donor perspective along this axis, or from the recipient perspective along the x-axis here. So, for example, different ways of interpreting it. Right, we can sit on one specific recipient frequency and just see where do we get energy transfer. And here, like the highest peak is here and is red, right? So this means is that the first higher harmonic receives energy from the vortex shedding, right? The first higher harmonic here and its donor is the vortex shedding and it receives energy. It's red. And what we can see here, so that's classical forward cascade. And the first higher harmonic gives energy to the second higher harmonic, right? Classical forward energy cascade stuff. On this line, we can interpret the production as mean as the donor. What does this mean? It's red, all red. The harmonics get energy from the mean. Along this axis, we can interpret it the other way around, mean as the recipient, but they're all blue, or this one is blue. These one are faint blue, you can't even see them. This means the same thing, just the other way around. That the mean gives energy to the harmonics. Now we can look at the structures at one specific triad frequency triad. So this one is the vortex shedding to the first higher harmonic, right? So the fundamental gets created. We should never say kind of created, right? Because it's a chicken and egg problem, right? You can never say there's no causality ever here, right? So everything happens kind of simultaneously in our spectral world. So we see what we see is the self-interaction of, right, the catalyst frequency. We can go down here, right? That's the fundamental itself, or negative itself, the conjugate, right? It's the fundamental interacting with its own conjugate to produce the first higher harmonic, right? And it produces and it gives energy, right? So we get net energy flux into the higher harmonic. The method also gives us the transfer fields. That's what we call it. This is where the energy transfer is happening. It's not just one number; it's an actual field, right? And the energy, most of it goes from the fundamental to the higher harmonic in this kind of separation region downstream of the cylinder here. Right, so this is kind of the next level. This is the first higher harmonic to the second higher harmonic. Again, red, forward energy transfer. This one here is interesting, the faint blue, because that points in the other direction. That's an inverse phenomenon. That is backscatter from a higher frequency to a lower frequency. And that is well described in the literature. This is what kind of always happens in all of these shear flows. And it's very interesting. So we can't fully have done it with really good intuition why this happens and why it happens at a certain kind of harmonic number. But it always happens. It's kind of nature's way to kind of close the whole system. Because what I'm not going to talk about in this talk because of time is what these you can't really see them, right? But what these hexagons here mean. There is 3 laws of conservation of energy. It's conserved between mode pairs. It's conserved between 6 mode pairs on each of these hexagon and over the entire hexagon and globally, right? So the energy is just moved around, but it stays within these shells. It's very interesting. And these are 1940s results from Kalman or whoever derived this stuff. But we can see that the vortex shedding actually receives energy from the second harmonic, right? So we have to go down the forward cascade a while to find backscatter into the fundamental. And where does it happen? One of these kind of shear layer regions between the bypass flow and the separation region. Okay, this one is the same one on the other way around, right? So these just flipped along this axis, right? So these have exactly the same absolute value, just different signs. So we can always explain, it's the same explanation, it's just that the recipient and the donor, they just change who they are, they just change roles. What's really interesting, the transfer fields, if I go back, they look very different. Nothing to do with each other, but if you integrate over them, you get the same value, just with different signs. So that's also a nice property we were able to show. So that's a conserved pair. This is just like an interesting little anecdote hidden in here. This is advection of the fundamental by itself. Everything is nonlinear, so strange things happen. The vortex shedding can induce velocity on itself, and it does so by slowing itself down. So things you see little dips in the fields, and that is nonlinear self-interaction, a nonlinear interaction of the vortex shedding mode. Okay, here's a more complex example to just really show the capabilities of this mode for now for proper turbulent flow. It gets a little trickier. That also is 3-dimensional. So that's work done by Eden based on a database from our USP Brazilian collaborators. I'm not going to talk a lot about the physics. I'm just going to mention that there's a lot going on in open cavities. That's where the Air Force, like, it's a canonical example for a bay, right? Any type of bay that opens or closes on an airplane. That's why they're interested. And what happens is you get a shear layer instability. That flapping shear layer, the carbon helmet, hits the back edge it sends acoustic waves upstream, and these can lock into a kind of reinforcing loop, and you get a global instability. You get a mode, and then you see spectra, peaks and spectra. There's also this large recirculation region, which in itself is a mode that you can find from linear theory. And then these two also interact. So that makes it a really interesting example. So if we just take a bandpass, just a slice in the shear layer, or a slice, right, along a strip in the shear layer, we take a bandpass filter that focuses on the fundamental oscillation frequency of the cavity and the very low frequencies, and we get this kind of really interesting. I think this is actually raw data, right? So if we just look at the raw data, we get this really interesting time trace where we see this band structure. This is the fundamental, they're called Rossiter instability of the shear layer, the roll up. But then it's modular. You see the slow meandering, right? You see these kind of street-like structures. And these are these centrifugal bands at very low frequencies, and we can separate these by just using narrow bandpass filters that we put at these frequency bands. And of course, we're interested in the interaction of these different structures. Right, so here's an animation of what they look like. Rossiter is that vortical instability, and the centrifugal, they're slowly rolling and they're creating these street-like structures. This is just a power spectrum. This is an SPOD power spectrum. So these are SPOD modes, and we right. So this DNS was computed periodically in the periodic boundary conditions in Z. So we can just separate out there's no loss of generality. We can just take the Fourier transform in the span-wise direction and look at the different components. I think sometimes call them beta, one sometimes Z. Right, and these are the leading spectra. So the first one, this is the 0, so nothing changes in span. Right, and with this high peak here, that is that Rossiter peak, that is this fundamental instability wave. Then at the first wave number, right, we pick one wave in, we get this spectrum with this peak, and so on, right? Green, I'm going to use this color code for the rest of these examples, right? So now we fit 2 waves in there, and so on and so forth. So now, what we have to look at, here's again the overview with the higher modes. You classify them, what they are, and so on. But what's interesting here is now the vanilla TOD doesn't cut it anymore because now we have different symmetries. This is just a simple periodic symmetry. We also use this for examples with O-type symmetry, with different D-type symmetries. We just have to mirror reflectional symmetries. So then you have to look at you can look at the interactions of the different symmetry components, right? How does energy go from a structure that looks like this and that is periodic in span to that is homogeneous in span, non-varying in span? How does this interact with a very low frequency structure with something that is oscillatory, that has a finite wave number and Z? So these are the type of questions we can answer using a cross-triadic orthogonal decomposition. Not going to talk about this. This is just basically what the TOD gives us. It's a blessing and a curse at the same time. So I'm not going to talk about any of this. I just call it the triad catalog. So what it does, it dissects the flow into all of these components. It tells us how they're all interactive. Gives us this huge catalog that we can play with. And again, it's a curse because it makes for very boring talks. Like the first few times, everybody fell asleep because it's just, oh, and this to this and this to this, and these are the structures. But you know, from a model order reduction and modeling perspective, I think it's a gold mine, right? And we have the preservation, all of these conservative properties and so on. So this is what it gives us. Just one last example, right? So on this data, because it just looks so spectacular, this example now, right? Maybe you're interested in now on these two axes, we have 2 different symmetry components, right? The donor frequency is in the span-wise not varying in the 0, and the recipient is in 3. And let's say we're interested in, well, where does this peak come from, right? Well, it comes from the Rossiter mode interacting with the negative, the conjugate of this small peak here, which is also natural instability, linear instability of the slow rolling structure, right? So we see the slow roller interacting with this Rossiter Kelvin-Helmholtz type instability through this very complicated flow field to pump energy from the Rossiter into structures that have this small inclination angle. And that's kind of interesting because there's like tons of papers where people describe the slowly meandering behavior of these waves. And this is exactly the explanation. Right? So the nonlinearity, it creates these oblique waves that then are slowly varying their phases and leading to this kind of meandering snaking structures. Okay, this is an overview. There's the paper should be, it's an archive forever, but it took 100 years, so that should be out soon, right? It's a new modal decomposition that uses a bunch of tricks to gives us modes that triadic interact. That gives us the energy transfer between these modes. And I really hope that this is a new route to nonlinear reduced order modeling because it's all baked in, it's all quantified already. We don't have to rediscover it. This in the frequency domain makes it also interesting. And so it screams, and it has two bases, so kind of screams Petrov-Galerkin in a way. So that's something we're going to look into in the future. That's the end of the main part that's the end of my talk. The last slide, no worries. The last slide is just a little sales pitch. That is something that I put together with Aaron Town from Michigan, Ricardo Villanueva, Adrian Lozano, and Scott Dawson from IIT. It's a data-driven reduced order modeling kind of challenge. I think that would be like nice topics for master students, or if you just have a method and you want to apply this on the side, if you just want to pitch this against other methods, because for each of these, we have sub-challenges for each. We have compression, 2D, 3D, we have forecasting, parametric is this simple example, and non-parametric for the fully turbulent. For actually it's that PIV data that I showed you that we used here, the experimental data. That's the forecasting, and we have sensing, right, from limited measurements. We want to make forecasts at other places in space. And for each of these, we provide two data baseline methods in MATLAB or Python. I think we all have MATLAB at least. For forecasting, for example, there is good old DMD and there is LSTMs. Right? There's always one kind of classical and one machine learning benchmark, and then you can just see, well, does my method produce better curves? And the goodie is that we're going to have a virtual issue. So and we're going to have dedicated invited sessions at SciTech and aviation meetings where you can present and put that in your CV. All right, that was the pitch. Go back to the topic, and that was it.
Thank you so much, Oliver. Really exciting set of topics. We'll first take any questions here in the audience in person. Yes.
Have you looked at the cavity flow where it's sufficiently narrow that there's no roll line? You know, Garit found that compared with the boundary layer thickness, that separation, if the cavity is narrow enough, there's a weird kind of stabilization where you inhibit any rotation roll up.
But there must be, right? Because in the limit it's 0. Yeah. No, we have not, right? So I kind of gave up on producing my own data. So we get the DNS database from our collaborators, and the measurements with they probably couldn't even measure this, right? The Reynolds number becomes so tiny there. So no, we have not looked at this.
On that topic, you mentioned that data, the physical data, the experimental data had noise, and then you use the widening filter. I wonder how that couples, if there is any type of limitations imposed by the upstream condition on your filter, or the opposite, you take advantage of that for your filter or anything like that.
I think it's kind of separated in the sense that we heavily truncate the modal basis. And these spectral methods, they are extremely good at putting everything that is noise into the higher mode. So we chop those off and then we only model the kind of more deterministic dynamics. So I think we kind of circumvented this problem.
Okay. But what if the upstream is not really noise? It looks like noise because you're not fully resolving it, but you have, as Bob mentioned, you have boundary layer, you may have curvature, so you may have some dynamics there that are under resolved.
Yeah.
And then if you chop them off, then maybe you kind of throw in the baby with the water bath type of thing, or so you want to conserve some of that, but not.
But then you hope that they end up in the residual and get modeled, right? Either in the first or second level residual, right? If not, your model is completely off, and right.
But then you're applying the filter to the residual, right?
Yes.
To model the residual.
Yes. Yeah. Right. So. I mean, what you're talking about, that's by definition very small scale, right? So that really depends on your engineering problem. Where are you interested in this? Maybe, maybe if you usually we integrate it over, we're interested in averages, right? But this would just be a trend or something. So, or we're interested in large fluctuations, which are frequency peaks, which we're resolving well.
Thank you.
Yeah.
Yes, in back.
With the TOD model, can you reproduce the Kolmogorov scaling in the testing?
Yeah. So it's not Kolmogorov because it's now a triple correlation, but there is also some papers from the 60s, Herrick, I think, who derived the isotropic turbulence theoretical bispectrum, and yes, we hit it. We put it in. I didn't put it in here. It looks really interesting. If you apply this method to homogeneous turbulence in a cube, classical DNS, we get ultra clean spectra. It is absolutely smooth. It works beautifully. It predicts the theoretical slopes, but the fields are a mess. And the energy transfer happens super locally, which is also an old theoretical finding, and it really highlights this. That the actual transfer happens not in an integral, in an integral way we see it, but it really happens at very small, at very, very fine scales. So structures, no. All statistics, yes.
Any other questions in the room? There's a question on Zoom asking why the SVD does not exist, converges numerically, or I guess it doesn't decay like fast, it decays slowly.
Yeah, I mean, it always exists, right? So maybe we're just very low rank. Maybe our data is super redundant or way too noisy, right? Then we truncate this off. What's the last part of the?
Yeah, I guess the follow-up was like, what if it decays extremely slowly?
Yeah, well, then we just have a physical problem that is extremely hard to model, right? So then that kind of goes back to your question too, right? So do we need to model isotropic turbulence? Kind of all engineering problems that are hard and interesting because they have something dynamic going on that we want to model.
I have a quick question. So for the TOD, you're saying that this was specifically for Navier-Stokes because you have like this quadratic term. Could this be applied to other systems that have quadratic terms, and does it only work for quadratic systems? Would it make sense to even consider like other systems?
Yes and yes. So it works for other systems, but you would have to plug in those equations, right? So the gradient might move around, right? You might have different conservative properties. You would have to specialize it, and I think the code we're going to upload, you can actually specialize it. You can piece together your terms and make whatever you want. The second, if it's non-quadratic, then it's different. Then you need, if you have, that's very rare, right? So I think there's some plasma physics where you have kind of quadruple correlations. Then you have to look at a tri-spectrum that gets really tricky. And there's some kind of Navier-Stokes, shallow water waves, for example, right? That they also have this kind of I don't even know what they're called, cubic interactions, right? But yeah, then you have to specialize this, and then it gets like really messy. Then you have three-dimensional spectra.
Yeah.
It's possible.
Okay, great. Any last questions? Okay.
So one last question. I'm curious about the computational time for these because with DNS, like the stuff that Srinivasan and collaborators have done with homogeneous isotropic turbulence, it just takes forever to run those DNS simulations. How long would something like this take?
Did you run the TOD or
I guess
the stochastic?
whichever the homogeneous isotropic turbulence one was.
Well, I mean, the TOD, this is all post-processing on steroids, right? So the DNS is done. There's no, right? This is purely data-driven. There's no operator anymore. So, but yeah, you have to fit that in memory. With everything spectral estimation, you can always, there's different methods. And the simplest trick you can always do, there's a kind of hierarchy of tricks. Okay, here's the simplest trick is compute each block individually, save only a few Fourier components you're interested in. Right, that all reduces drastically the problem. If that's not a good option, you can always use a running covariance estimate. Right, so you can use oh god, what's it called? Yeah, just the running covariance. Right, you can just combine a running covariance estimate with the kind of like a Krylov type method where you snap on a new data vector. That also, we have a paper on this, but it's old, right? You can just basically add on new data, then reorthogonalize, Schmidt it, and so on, right? So you can do it in a streaming way. And then what we usually do is just find a workstation with enough memory, right? Buy another terabyte of memory and don't waste your lifetime on other stuff.
Okay. Well, thank you again, Oliver. This is really amazing. And Oliver will be around today for a bit if you want to follow up with any additional questions. Let's thank you, speaker again.